In this lecture, we're going to go over throttling devices. They're devices that achieve a reduction in pressure by introducing a restriction in a flow line. You can do this by a partially closed valve or using a porous plug. For a control volume that encases a throttling device, the flow work is the only work that occurs. So there's no other moving parts. There's no significant heat transfer between the surroundings and the throttling device. The changes in potential energy at the inlet and outlet are also negligible. So our energy balance reduces to our change in enthalpy plus our change in kinetic energy is equal to 0. Although you can get high velocities occurring in the vicinity of the restriction, if you take measurements far enough upstream and downstream, the changes in specific kinetic energy of the flow are small and can be neglected. So with that additional simplification, we have that H2 is equal to H1, where P2 is less than P1. We're going to do a few examples. We have a supply line carries a two-phase liquid vapor mixture of steam at 300 psi. A small fraction of the flow in the line is diverted through a throttling calorimeter and is exhausted to atmosphere at 14.7 psi. The temperature of the exhaust stream is measured as 250 degrees Fahrenheit. We want to determine the quality of the supply line. So we have state 1 is two-phase. We have T1 is equal to 417.43 degrees Fahrenheit. At state 2, we know that H1 is equal to H2. We have P2 is equal to 14.7 psi. At which point Tsat is equal to 211.99. So T2 is greater than Tsat. So we have superheated. We get H2 is equal to 1168.8 BTU per pound. At state 1, we have HF is equal to 394.1 BTUs per pound, and HG is equal to 1203.9 BTUs per pound. So our quality is H2 minus HF for HG minus HF, which equals 1168.8 minus 394.1 over 1203.9. We have our quality is 95.7%. The second example we're going to look at is we have a valve and a steam turbine that operate in series. The steam is flowing through the valve, undergoes a throttling process. At the valve inlet, the conditions are 600 psi and 800 degrees Fahrenheit. At the valve exit, corresponding to the turbine inlet, the pressure is 300 psi. At the turbine exit, the pressure is 5 psi and the temperature is 200 degrees Fahrenheit. Stray heat transfer and kinetic and potential energy effects can be ignored. We want to determine the work developed by the turbine and BTU per pound of steam flowing. So we have a one inlet, one outlet system, so we just have our mass flow rate is equal to constant. If we do our energy balance, we have 0 is equal to Q minus W. There's no kinetic, there's no potential, there's no heat. So our work per unit mass is equal to our change in enthalpy. Or these should be state 3s. We don't need state 2 because of the boundary that we chose on our diagram. So our work is H1 minus H3. For state 1, we have T sat is equals 486.33. Our temperature is greater than our saturation temperature, so we are superheated. H1 is equal to 1407.6, and for state 3, we have T sat is equal to 170.3. Our temperature is still greater than our saturation temperature, so we're still superheated. And H3 is equal so work per unit mass is equal to 259 BTUs per pound. We're going to note that H1 is equal to H2, but P2 is less than P1. In our next lecture, we're going to go over systems of components.